let A and B be row equivalent matrices. Then the row space of A is equal to the row space of B. In other words, the span of the rows of A is equal to the span of the rows of B. So let's go ahead and prove this. Proof. Since A and B are row equivalent, that means that B is gotten from A by elementary row operations. So suppose B comes from A via elementary row operations. Each operation expresses the new row as a linear combination of the old rows. So, in particular, every row of B is a linear combination of the rows of A. In other words, the row space of B is contained in the row space of A. Reversing the argument, shows that the row space of A is contained in the row space of B. But if the row space of B is contained in the row space of A, which itself is contained in the row space of B, that means that the row space of A must equal the row space of B. Therefore, the row space of A must equal the row space of B. Consider this example here. You might notice that the rows of this matrix are exactly the vectors that I had you look at in the question following the previous video. I'm going to show you how we can use this theorem to give you another way, a more straightforward way to determine a basis for the row space of this matrix for the span of those three vectors. So we can row reduce, Gauss-Jordan elimination, to get a matrix B, which is 1, 0, 2/3, 0, 1, 7/3, 0, 0, 0. Then by what we just talked about in this theorem, so by theorem 3.20, the row space of A is exactly the row space of B. Okay, but by just inspecting this matrix B, we can see that the span of the first two rows of B spans the row space, because 0 doesn't, we can always get rid of 0. And these first two rows are linearly independent. So therefore, 1, 0, 2/3, and 0, 1, 7/3 forms a basis for the row space of A, because it forms a basis for the row space of B, and the row space of B is equal to the row space of A. The same argument that we used to determine that these two vectors form a basis for the row space of this row echelon form matrix B can be used to show the following theorem. If R is a matrix in row echelon form, then its non-zero rows form a basis for the row space of R. I'm not going to go and prove this, but I want you to try and do it. Remember, there's two things you have to prove. You have to prove that the span of these non-zero rows is the span of all the rows, and that these non-zero rows are linearly independent. Finally, we get to the actual row method. And really, this is exactly what we did in the example. So we're given a subspace S spanned by vectors v1 through vk. And our goal is to find a basis for S. Here are the steps of the row method that will allow you to do this. Step 1, let me put that in blue. Step 1, form the matrix A whose rows are our given vectors. Step 2, reduce the matrix A to row echelon form. Call the row echelon form R. Three, then use that S is equal to the row of A, the row space of A, which is equal to the row space of R, and this is by theorem 3.20, to conclude that the non-zero rows of R form a basis for the row space of A, or in other words, for S. I do want to point out, though, using the row method, the vectors you get are usually different from the vectors that you start with. You can see that by looking at the last example. But what if we want to find a basis for S which just omits some of the given vectors? We'll see how to do that in the next video using the column method.